Good morning, everyone. This is Mr. Keppel. Today I'm here with my IBSL Year 2 students. We'll be talking about astrophysics and mainly the Hertzsprung-Russell diagram. Before we get into that, I just kind of want to go over a few concepts that were in the previous lesson on stellar characteristics and like looking at the spectra of the light from stars to be able to figure things out. Here's a picture of a globular cluster. What a globular cluster is, it's a cluster of, like some millions of stars. They're just all kind of clustered together, almost like a beehive. Well, this isn't a star. Every single one of these spots, single speck in this image, those are individual stars, and they're all just kind of clumped together. It's called a star cluster. They're clumped together by gravity, like pulling all these stars together. What we're really looking at here is like a million stars. So what we can do is we can make measures of the apparent brightness of each star. So we can point our telescope at the location of each star in this image, and we can, using sensitive computer equipment, we can determine what the apparent brightness of each star is. And then we can also, wait, what does it say? From measurements of apparent brightness and distance, right? And so we can also use the parallax method or other techniques to determine the distance to those stars. And from that, you can determine the luminosity. So the way that that works is the luminosity is, and this is a review from the video that I had you guys watch last time. The luminosity is 4 pi r, well, r is actually going to be d squared times the brightness. So that's the luminosity of a star. And so the 4 pi d squared is just the idea that, there's a star here, and what it's doing is it's radiating energy outward. And then all across this whole area there is the area where the energy is spread out. And then if we're here on the Earth, then realize that the distance we are away from the star is the radius of the sphere that energy from the star is being spread out across. And so that's why we use d there instead of r, because it's really it's the radius of this gigantic sphere where the star is at the center, and then we on the Earth are at the edge of that sphere. But it's better, it's more, it's just easier to use d for that distance to the star, and that's was supposed to be discussed in the video that we watched. So I'm just kind of going over some of those ideas. All right, next. From the emission spectrum, we determine the surface temperature. And so that was this equation. I'll show it to you guys real quick. It's in the IB data booklet. Nope, not that one. Man, I thought that one was first. Here it is. This is the Wien's law, that the maximum wavelength in the emission spectrum times the temperature is 2.9 times 10 negative 3. So I'm going to write that down. So Wien's law says that temperature times, I think I did that backwards, lambda max times the temperature is equal to 2.9 times 10 to the negative 3 meter kelvins. So what I'm trying to get at here is that we can measure the luminosity of a star. Or we can't merely measure it, but what we can do is we can determine it. So we can figure out the luminosity if we know how far away the star is and we know what its apparent brightness is. We can find the luminosity. And we can determine the temperature of a star by observing the maximum wavelength in the spectrum. Remember, the spectrum is where it looks like, I'll just try to remind you guys what that looks like. So you've got intensity up here versus the wavelength, and it makes that graph where it's kind of like that. And you just see like where is the peak, and then you bring it down, and then that's the lambda max. And so we've talked about that before. I'm just giving you guys a jogging your memory. Okay, so here's what's up.
There has to be a mistake. There's less than one of me in the equation.
Meter Kelvin. What's a meter Kelvin? Yeah, it's a weird unit. Okay, so here's the question. What happens if we plot this data? So what happens if we take the luminosities that we measure and we plot that against the temperature of the star? And you end up getting this plot here. So all of these stars in this cluster, we're going to plot all of them. We're going to measure every single pixel on this picture. We're going to measure the luminosity, or we're going to determine the luminosity and the temperature for every single pixel. And if you do that, you create this graph, which is called a Hertzsprung-Russell diagram. And what you'll see is that a very clear pattern emerges, which shows that there is a correlation between the luminosity here and the temperature down here. You can also notice those spectral classifications down below. If you remember, it's O, be a fine guy, and kiss me. Is A, B, A. Yeah, those are the spectral classifications of the star, which are roughly related to the temperature of the star. Well, I mean, not roughly, but they are. They're related to the temperature of the star. So OBAFGKM. This is called a Hertzsprung-Russell diagram. And so you notice that there's like the stars just can't be anywhere. Like there's actually these like groupings of like where these stars appear to be. Like there's these clusters within this diagram. Now remember, these aren't like the physical locations of these stars. This is just the plot of these mathematical quantities, the luminosity and the temperature. And so what we're noticing is like stars can't just be at any random place. Like there's actually sort of this pattern, there's this trend to where we find the stars on this luminosity against temperature graph. There's a few things you have to take note with an HR diagram. Number one, the luminosity is given in terms of solar units, which are the luminosity of the sun. So we call that circle with a dot on it as a subscript. That's called the luminosity of the sun. The solar luminosity is 3.8 times 10 to the 26th watts. So that's called the solar luminosity. So if you find a star that's at 100 on this diagram, then it would actually have 100 times this luminosity of the sun. Secondly, temperature decreases to the right. So this is really strange. So notice that the temperature actually gets smaller when you go to the right. So it's a reversed chart. So instead of getting hotter, instead of the numbers increasing to the right, they're actually decreasing to the right. So that means that the hotter stars are over here and the colder stars are over here. And that's a weird, I don't know why we do it that way. That's how it's done. And then the last thing is that both scales are not linear. So if you notice here, from this axis to, or from the axis to this dot here, that's a distance, that's 20,000 distance or difference. Whereas here to here is only a 4,000 difference. So this is not a linear scale. If you go even further, this is a 3,000 distance. Because a linear scale, each spacing would be the same on a linear scale. This is not a linear scale. The bottom scale is just it's messed up because you're doing it based off these spectral classifications. So there's really no like set scale to it. But the vertical axis actually makes perfect sense. So you can notice like from here to here is times 100, and from here to here is another times 100. So we can clearly see that this is what's called a log scale. So logs, maybe you guys have heard a lot about log scales recently because that's how we plot a lot of the pandemic data is with logarithmic scales. Okay, so that's the HR diagram. So it's a really helpful way of classifying stars, of sort of seeing the trends and patterns within stars. And we're going to be spending the entire week talking about this diagram. So we're just getting started on this today. So here's sort of the essential question for the lesson today. It appears that stars are limited to exist only at certain luminosities and temperatures. For instance, you don't find any stars here. Stars with this luminosity and this temperature, they don't seem to exist. And so the question is why? Like, why are stars restricted to only be in these certain strips, like these certain bands? Like, why are there only certain values of luminosity and temperature that are allowed? Why not any value? And the answer to that question is really complicated, and we have to talk a little bit more about some stuff. Okay, first off, here's a really cool graph. I stole this out of our textbook. And so, what was I going to say? Oh yeah, you could just see like all the different stars here. So like there's the sun, so that's where you find the sun on this diagram. Maybe I should use like a brighter color. There's the sun, and notice that the sun is like right sort of in the center, right? Because it has luminosity of 1 and it has temperature of 6,000. So the sun is kind of like the reference in the middle. Then you can see there's this thing called the main sequence, which is this green strip here. That's called the main sequence because that's like where most stars lie. It's not like, don't think of it like a sequence like one after the other. It's just the sequence of like, this is where stars spend most of their lives. Most of the life of a star is going to be spent somewhere on this green line. What else? Okay, so remember the Stefan-Boltzmann law? This was when we talked about black body emissions. For a star, if a star is a spherical shape, then realize that when you go to plug in the area in the Stefan-Boltzmann equation, the area is just 4 pi squared r squared. So that's I don't know why I put pi squared. It's supposed to be, isn't it just 4 pi r squared? I don't think it's supposed to be pi squared. I don't know why I did that. Anyway, it's 4 pi r squared. There we go. Okay, so you just take the radius of the star, and then, if it's emitting power out, right, it's releasing energy out of it, we can find the power output from the star with this equation. So use the Stefan-Boltzmann constant, 4 pi r squared t to the 4th power. So it's pretty obvious to think about like why, because what do we call power for a star? Like, do you guys know what power of a star is called? We don't call it power. I'm asking you guys that are listening. Um, what do we call the power output of a star? We don't call it power. Do you know what we call it? Was it in the video? I think it was. No?
Oh, cricky.
Does that help? It's luminosity.
As soon as I was about to say it.
It was the communication lag. It was internet lag. So the luminosity is the power. What's up?
I can't see the stream right now. Oh, it like keeps freezing and then updating, and then it's really being really weird right now
Okay,
for me.
I can try stop streaming. I'll restart the stream.
There we go.
All right, so remember that the power output of a star is called the luminosity of a star. So we don't use the word power anymore, we use the word luminosity. And so realize that there are two things that affect the luminosity of a star. Remember, this is my mistake. This shouldn't be squared up. Okay, there are two things that affect the luminosity of a star. There's the radius and there's the temperature. And so it makes sense then that there'd be this relationship between luminosity and temperature, that those two quantities would be related. And we can see that on the chart over here. So that's why the luminosity and the temperature are related. It makes sense because of the Stefan-Boltzmann law. Also, notice that the radius then is going to be in there as well. And so you can create these lines, that's what these dotted lines are, of constant radius. And so that's another helpful way of interpreting this diagram is if you keep a radius of like the sun, then you can see that you get all these different, this line right here is stars that have the same size as the sun. And so if you're the same size as the sun, you'll be along that line. All right, note further, the lines of constant radius can be added. Okay, so just if you ever see those horizontal, or not horizontal, but if you ever see those diagonal lines on an HR diagram, those are just lines of constant radius. So not only can you determine like the luminosity and the temperature from this graph, but you can also determine the radius of the star, which is cool. Okay, check this out. Here's a diagram of the sun as we understand it. So the main idea that I want you guys to get at here is the core. The core is where all the energy is coming out from that core. All that energy from the nuclear reactions inside the sun are radiating outward from the core. And so we're going to answer the question of why only certain size stars can exist. Okay, this is the fusion process that occurs within the sun. It's called the proton-proton fusion cycle. So basically what happens is the sun is so hot. There's so much pressure inside the core of the sun that we can actually overcome the electric repulsion barrier between two protons. So normally two protons come together, they'll repel each other. But if they're moving fast enough and they have enough energy, they can actually collide with each other and fuse together. And so that's what's happening inside the sun. So first up, two hydrogens get close enough together that they can fuse into hydrogen 2. And when that happens, you'll have a positron emission. And so that's what's going on here, is that in this region of the diagram here, the two hydrogens are forming hydrogen 2. Then you just take that hydrogen 2 plus another stray proton, and then you can make helium 3. And so that's what's going on in this, that's going on in the second part of the chain. And then the last part of the chain is to take two hydrogen heliums, two helium 3s, there you go, I finally said it, two helium 3s, and turn those into helium 2s with two protons being ejected from that. And then that's what's going on in this last part of the diagram there. Energy is released at each step in this process. There's energy coming out of here, and that's the energy that's coming out of the sun. So all this energy here is coming out of these three fusion reactions. So energy is carried away from the core of the star by photons and also neutrinos. If you remember up here, there were a couple of there was a neutrino there that came out, and then photons. So these are the things that are carrying the energy out from the sun. As the photons move outwards, they collide with the surrounding material, creating a radiation pressure. And so that's what's happening here, is as these photons from the core start to fly out, if you've got a photon in here and it's flying out from the core, how do I want to draw this? I've got a photon right here, and it's flying out from the core. So it's going to exert this like pressure, like this. It's going to push into the surrounding material within the star, and that's going to try to expand the star. The star is going to try to grow and like get larger from the force of all these photons and all these neutrinos, like pushing out from the core of the star. Now, why doesn't the core collapse? Well, because there's also gravity. So the star has its own gravitational pressure. All the mass in the star pulling together. And so what happens is the star ends up having this equilibrium where the radiation pressure from the photons pushing out is equal to the gravitational pressure of the mass of the star pulling in. And then this, if you think about this more deeply, this is really cool. Okay, so the luminosity indicates the strength of the radiation pressure. So that outward pressure that the star is exerting from the radiation pressure, that's a result of the luminosity of the star. And then think about the inward pressure due to gravity is a result of the mass of the star. And so if we make a graph of luminosity versus mass, we end up finding that there's a really strong relationship between luminosity and mass. And you might be wondering, what the heck is this log stuff? Well, the logs are just there because it's not a linear relationship. It's an exponential relationship. So anyway, this leads us to this rough approximation. So you can see that the slope of this line here, of this fit, notice that it breaks down at the edges here. But for most stars, and it ends up being stars that are on the main sequence, you end up having this relationship, is that if you plot the L, I'm just going to call this L. If we do L against mass, it ends up being to the 3.5 power. And that's what this 3.95 is. So I'll prove this to you guys real quick. So if we take the log of both sides, so if I take log of L and I take log of, I don't know why I put lag. It's because I was thinking about the stream. If I take, why did I put a capital L? So if we take log of both sides, log of L and then log of M to the 3.5. And then what ends up happening is you get this, you get log of L. I did it again, I keep doing that. Log of L, and then one of the rules for logs is when you have a base to a power, the power actually comes out in front. So 3.5 log of M. And so now you can see why this graph, this is the y-axis, log of L, that's the y-axis, and then this is the x-axis. And so then you can see that this looks like the equation of a line, y equals mx. And so that means the 3.5 is just your slope. And so that's why the slope was it's 3.95, but we're going to end up using 3.5. Okay, so there it is. That's all I wanted to show you guys from this graph here. So just realize that it makes sense that because of like the equilibrium that's going on within a star, that this relationship would end up being true. That based on the luminosity of a star, you can determine the mass of the star, because if it were any more massive, it would collapse under its gravitational pressure. And if it were any more luminous, it would blow up from its radiation pressure. And so that answers the question of why do we find stars only in certain places? Well, because based on the physics of this equilibrium, of this battle between the radiation pressure and the gravitational pressure, stars are only stable with certain amounts, certain configurations of luminosity. And that's why we end up getting this strong relationship here, this correlation that forms this diagram. What questions do you guys have for me about any of the stuff I've talked about here?
So it has to be proportional relationship between the luminosity of the star and the mass of the star in order for them to be stable.
Yep, exactly right. All right, that's the end of part 1 of this video.
Mr. Keppel.
What's up?
My dad has a question.
Yeah.
If the light is bent all over creation from such a long distance by all sorts of various forces, how is the luminosity accuracy?
Oh, so we have super sensitive equipment, and so the luminosity is literally gauging the energy that you're receiving. And so you're right that there is a lot of random fluctuations and things you have to take into account. So the accuracy is not good. What I should say is the precision's not good, but the accuracy is good. So we can take into account, like, we can put error bars on all of our measurements and be confident within a certain region, but interval. But you're right that like we're not going to have very precise numbers. So like if you go look up the luminosity of a star, there'll be huge error bars on it. Like it'll be really like we can't really lock it down perfectly well. But yeah, you're totally correct in that thought process. But our instruments are super sensitive, and we can pick up even like the faintest star in the sky. We can still pick it up. Like it's pretty amazing to think about how we can pick out a single pixel in this image, like this one pixel right there, and we can look at that pixel and we can determine the luminosity and the temperature of that star from that single pixel of data, which is crazy to think about. Ethan, your mic is still open. We're getting some noise. Okay, we're good. Okay, so we're going to do the handout now. So you guys can switch over to the handout. So we're going to start doing some calculations here. Looks like I'm way over on time.
Altair.
Yeah.
Why
What's
are
up?
we learning about an assassin star?
Say again?
Altair.
Oh, yeah,
The,
I see what you're saying. I picked this star because it's a really cool star. I'll tell you why. So the star Altair or Altair is the 12th brightest star in the night sky. It is an A-type main sequence star with an apparent visual magnitude of 0.77. It is 16.7 light years from the sun and is one of the closest stars visible to the naked eye. Another thing about Altair that's really interesting is it spins super fast, and so it's actually not a spherical star. That it's actually like oblate, like an oblate spheroid, like it's bulging out because it's spinning so fast. Okay, using this available data, determine the following. What's the apparent brightness of Altair? So in the video I had you guys watch last week, it was I don't think they had this equation in here, but this is the apparent brightness of a star, and then this is the magnitude of the star. I think they talked a little bit about the log scales and stuff like that. So what we're going to do is just calculate the brightness of the apparent brightness of Altair. Now, real quick, so you might remember this equation that the intensity of light or the intensity of a wave is the power divided by the area. That's still going to be true here, except in astrophysics, we use the apparent brightness to be the intensity, and we use the luminosity to be the power, and we use the area as a sphere. So that's 4 pi d squared. And so that's how things change. It's the same exact formula that we've been using since we talked about waves, like way back in topic 4, but we just changed things around because we're talking about stars now. We're specifically only talking about stars. So intensity becomes apparent brightness, power becomes luminosity, and the area is the surface area of a gigantic sphere where the star is at the center, and then our observation is at the edge of that giant imaginary sphere. Okay, so the magnitude of Altair is 0.77, so we want to find the apparent brightness of Altair. Okay, so the way we do that, I think I'm going to, let's see, I got to rearrange my setup here because I'm having trouble writing on the screen. Okay, so to find the brightness, we just have to take this 2.512 to the negative m power and multiply by b naught, where b naught is just this reference value. That's what gives it the apparent brightness. So you're not actually it's not the absolute brightness, it's the apparent brightness. So we're referencing it to some like standard reference number, which is that 2.5 times 10 to the negative 8. Okay, here we go. So the brightness of Altair is going to be 2.512 to the negative 0.77. And so that 0.77, that's the magnitude of Altair. So we don't give the apparent brightness of stars, we actually measure the magnitude using this equation. So like when you go to do a Google search of a star and you ask like how bright is Altair, it's going to say, oh, the magnitude is 0.77. They won't actually give you the apparent brightness in watts per square meter. They're going to give you the magnitude number instead. Then I just have to multiply by that reference value, which was 2.52 times 10 to the negative 8, and then that's watts per square meter. So if we want to find the actual apparent brightness of Altair, we have to do a little bit of math from that magnitude value. Notice that it's just taking that 0.77 and plugging in here. Everything else is constant. So it's very easy to create, a computer program that could go back and forth between these two things. So 2.512 raised to the negative 0.77. And then I'm going to take that number and multiply it by 2.52 times 10 to the negative 8. And I get the apparent brightness of Altair is 1.24 times 10 to the negative 8 watts per square meter. And you would expect to get a really, really small number for this because, the star is far away. It's 16.7 light years away. So the amount of energy per square meter that reaches us is going to be extremely small. So you imagine if you had like a 1 meter by 1 meter by 1 meter detector, like 1 meter by 1 meter by 1 meter by 1 meter detector, how much energy would be going through that square would be a ridiculously small number. So it makes sense that the brightness would be a really, really small number, the apparent brightness. Let's calculate the distance to Altair in meters. So we need to look up how far 1 light year is. So let's go to the data booklet. So that's here. So in the unit conversion section of our data booklet, we can look up, where is it? Here it is. 1 light year is right here. So 1 light year is 9.46 times 10 to the 15 meters. So back to here. So I put 9.46 times 10 to the 15 meters. Okay, now I want to find how far Altair is, and that's 16.7 light years. So I just have to multiply both sides of this equation by 16.7, and then I'll have the answer. So that's going to be 16.7 light years is equal to this number, 9.46 times 10 to the 15 times 16.7. And then if we do that, we find out that the distance to Altair, so that's little d, the distance to Altair, I'll do it over here. So I have, let's see, 9.46 times 10 to the 15. That's a light year in meters. And then 16.7 light years is 1.58. 1.58 times 10 to the 17 meters. Okay, now we want to find the luminosity of Altair, and so we are just going to use this equation right here, which says that the luminosity is the apparent brightness times 4 pi times the distance squared. And so we know what all those things are because we've calculated them. So the luminosity is 4 pi d squared times b. We've got the b up here, and we've got the distance down there, and we can just plug it all in, and then we'll find the luminosity of Altair. So here we go. So luminosity of Altair is going to be 4 pi times 1.58 times 10 to the 17. And then we have to square that. And then we're going to multiply it by the apparent brightness, which is 1.24 times 10 to the negative 8. So I've already got my distance in here. So all I have to do is just square that number and then multiply it by 4 pi. And then multiply that by 1.24 times 10 to the negative 8. And so here's the luminosity of Altair. The luminosity is, can I draw a nice looking L? Here, I'll try one more time. Luminosity is 3.89 times 10 to the 27, and then that's watts. So what will happen is, remember that this was watts per square meter, and then this was meters, and so you end up squaring that meters, and then that's meter squared, and so that cancels out and you just get watts. So that's the luminosity of Altair. The diagram to the right is an HR diagram with the main sequence indicated with the black curve. The surface temperature of Altair, didn't I change this? I thought I changed this, hold on. I think I'm showing you guys the old version of this file. This is the one I uploaded though, isn't it? Oh, jeez. I swear I changed this. I didn't change it, wow. Maybe I know I did. Hold on, I'm digging in here, guys. Give me a second. That's the wrong year. 2019, 2020, IB Physics, Astrophysics, HR diagrams. I know I changed this file. I guess I just didn't change it in the right place. This is the one that I wanted. I'm sorry, guys. Let me I uploaded the wrong file. This is what I get for not double checking it. Okay, this is where I want to be here. The diagram to the right is an HR diagram with the main sequence indicated with the black curve. Hopefully this doesn't mess you guys up too much. Okay, so this black curve is just the main sequence on the HR diagram. Locate Altair on the diagram. The sun's luminosity is 3.8 times 10 to the 26 watts. Okay, so the first we need to do is we need to figure out what the L over L solar is. That circle with the dot in it is the solar luminosity. So L over L solar for Altair. Well, we know what L of Altair is. We just calculated it. It was 3.9 times 10 to the 27 watts. And then we just want to divide by the luminosity of the sun, which is 3.8 times 10 to the 26th watts. And if we do that, we get, let's just call it, it's like 10.2. But let's just call it 10 is close enough. So we know that we're on the luminosity chart. We're like here, maybe a little bit above 10. That's where Altair is. And so if we go over from there, I'll do a straight line tool. If I go straight over from there, now Altair is on the main sequence. So that means that Altair should be right there where it hits this main sequence line. And if I drop down from there, we can estimate the temperature of Altair there. So this is where Altair is. I'll put a circle there. That's Altair. Estimate the temperature of Altair. So looking at this chart, this is really hard to do because this is 10,000 and this is 6,000. What the heck is right there? So I'd say that's about 8,000-ish. So we'll just go with 8,000 Kelvin. Remember, we're just estimating it. Like, we don't have a very good scale here. So we'll just say that the temperature of Altair is about 8,000 Kelvin. And now it says to determine the mass of Altair. Well, we have that relationship that the luminosity is proportional to the mass to the 3.5 power. And so from this, we can, instead of solving for L, we can solve for M. And so what you need to do is you need to take both sides to the 1 over 3.5 power. And then we get this that says that M is proportional to L to the 1 over 3.5. Now we know what L is for Altair. It's 10.2. We're going to use this in terms, if we plug in 10.2 as like the solar luminosity, like the luminosity compared to the sun, then we'll get the mass of Altair compared to the sun, which is a fine value to put in there. All right, so now all I have to do is just say that the mass is going to be equal to 10.2 to the 1 over 3.5, and then it's going to be mass of the sun. And so I'm using the mass of the sun there as my proportionality coefficient, changing the proportional to an equal. Okay, so now all I have to do is just do 10.2. Hello, calculator, please turn on. 10.2, and then raise that to the 1 over, wait, let me put a parenthesis here. So shift insert. Okay, let me put parenthesis. So 1 divided by 3.5. And so I get this, which is about 1.9. So this tells us that the mass of Altair is about 1 times more massive than the sun. And we got all of that from the HR diagram. And that's why the HR diagram is so useful, because if you know that a star is a main sequence star, you can find out so much about the star from this diagram. Like, all that we had up here was, I just looked this up on Wikipedia. We have the magnitude and we have the distance. And if we know the brightness of the star and we know the distance of the star, you can find out so much about it. You can find out the mass of the star, you can find out the temperature of the star. There's so much stuff that you can figure out just based on this HR diagram. Okay, that's it, guys. I'm going to stop the video here. If you're interested, I will upload a second video that will have the solutions to the back. But I wanted you guys to try and do the problems on the back on your own and then get stuck on it and then watch the video for the second part. All right, I'll see you guys later. Have a great day.